Alright guys, so today we are going to look at building and make sure that we know how to do things with boundedness. We can determine whether functions are even or odd. We can also determine limits, one-sided and two-sided limits. We'll look at discontinuities as well as inverses of functions. So let's get started here. So the first question is determine if the function is bounded above, bounded below, bounded or not bounded. So examples of bounded above, if I have absolute value function or a function that just simply ends at a point, that's all bounded above. Now if I have bounded below, you can flip those over. And these are bounded below. Now, completely bounded, good examples would be circle, simple trig function. Not bounded would be functions that don't end, so they go off to infinity or negative infinity on both sides, right? So quadratic functions are always bounded either above or below, so this polynomial to the second degree, it's bounded below. You can graph it to check it out. Looks like this, and as we can see, it doesn't go below that height. Here I have a rational, and they tend to look like this, but as you can see, there's no lowest low, there's no highest high, so this is natural log function looks like this, and it is unbounded. Definitely gets close to zero in terms of the x's, but it never stops going. There's an infinite place it goes to, and a negative infinity as it moves towards zero. Last one is absolute value, and it is bounded above. It's bounded above because it is negative. Okay. Just some simple questions there. Number 2 is determine if each function is odd, even, or neither. So justify your answer algebraically. So when we do that, we want to replace x with negative x. Replace all of our x's with negative x. Okay. This equals 3x to the 4th plus x squared minus 1. And this is even because all the signs of the x terms stay the same. So let's try b. Okay. So I have negative x to the 5th plus 2 times negative x cubed minus negative x squared. And I get negative x to the 5th, so there's a change. Negative 2x cubed is a change. Minus x squared, and there's no change. And this is neither because there are changes in signs, and then there are places where it remains the same. All right. So how do I attempt the second one? So it says suppose that the limit as x goes to 0 equals negative 1, and f of 0 equals 2. So it's defined here. So let's draw what this looks like. Let's draw what this looks like. So we have our graph, and I need the numbers. I need 0, and I need negative 1, I need negative 2, I need 1, and 2. So let's put these on our map here. And we have -1, 2, 1, and 2. All right. So says suppose as x goes towards 0, f of x equals -1. So right here, f of x equals -1. So I put a little hole there to denote that. It's this portion. All right. But we also have that f of 0, when x is 0 and y is 2, there's a point. So it's defined right here. And then it says f has a removable discontinuity. So a removable discontinuity could be a hole or a filled-in point. We're going to go with the hole at x equals 0. Then the limit as f of x goes to 0 is going to be, from the left, is going to be equal to this. This is a trick question. It's trying to ask you, is the limit where it's going to be as it moves, as it approaches from the left or the right, is it going to be equal to where it's defined, or is it going to be equal to where there's an established limit? And so let's say on a test they asked if the limit as 0 moves from the right of f of x, what it's going to equal? It's going to equal what the whole two-sided limit equals. Otherwise, it's wrong. All right? So make sure that you kind of get that. So suppose that the limit as x approaches 1 from the right of f of x equals 2, and the limit as x approaches 1 from the left is 5, and f of 1 equals 5. Which of the following must be true about f of x? Well, first of all, there has to be a break, because this is what it looks like. There has to be a break. So imagine that this is 1, right? From the left, I have a height of 5. So 5 is way up here. From the left, I have a height of 5. And my function might look something like that. From the right, I have a height of 2. So here's 2. Okay. Now, if you look, what I've told you over and over again, if there's two different heights, then the limit as a whole does not exist. All right? In fact, this function cannot be continuous. So this is f of x is continuous at x equals 1. That's incorrect. F of x has a removable discontinuity at x equals 1. That is incorrect. Because if it was removable, it would be continuous. It would be somewhat continuous. Like it would be connected. It would be like a hole. This is removable. Now, f of x has a jump discontinuity at x equals 1. This is absolutely correct. And f of x has infinite discontinuity at x equals 1, and that is incorrect. So just be mindful, look at the pages, practice some of those things that you were doing before. All right, it says evaluate the indicated limits of f. Here's our graph. So as the limit as x goes to negative infinity, so I'm going to start from the right and go towards negative infinity and see where the y values go, jump. And it looks like those y values are decreasing towards negative infinity. So that's how I look at it. I follow the path that I need towards my limit. Let's do as it goes to infinity. So from the left, I'm going towards infinity, right? Going towards infinity, I jump, keep going, and it looks like it stays at a height of 1. So that's good. All right, now we have the limit as x approaches -2 from the left. And as always, I like to circle what's going on at -2. So from the left, I am going up to 1, and I stop. From the right, I am going up to 4, a height of 4, and I stop. So just be mindful. And that creates a jump discontinuity. It creates an obvious break. All right, and lastly, at 1, we have 1. We have 1. Okay. So not a very not very hard at all. Okay, and on the right, I want you to practice this one on your own a little bit. See how you fare. I'll see if I can do an answer key for you. But that's additional practice for you. All right. So this is solve for a so that f is a continuous function. So I'm going to set this up here. When I do this, my rules are 1, set equations equal to each other. Okay. Number 2, identify x. 3, evaluate with x. 4, solve for a. Okay, so I'm going to set these equal to each other. X plus 7, this group, square root of it equals x minus a. Then I have square root, and x equals -3. Okay, equals -3 minus a. Get square root of 4 equals -3 minus a. Get 2 equals -3 minus a. Add 3 to both sides. 5 equals -a. To make this work, I'm going to put a 1 in front of that a, divide both sides by -1, and a equals -5. Now let's rewrite our equations here. We have f of x now equals square root of x plus 7. And in order to make this continuous, I must have x minus a -5. Okay? And x is less than -3 here. X is comma, greater than or equal to -3. Okay? Now, it says without using the identity function, find rules for f of x and g of x. So basically, we're decomposing functions here. Okay, so my inner is going to be the same group. It's x plus 1. My outer here, x cubed plus 2x. Keeping it simple. For b, my inner is the same group, 3x. My outer is sine of x minus x to the 4th plus 2. I'm done. Lastly, we want to look at inverse functions and one-to-one. All right? So inverse functions, you're just composing. First, you're going to see me insert x plus 1 into x. Then you're going to see me insert x squared plus 1 into this x over here. All right? But down here. But let's do x squared plus 1 first. So I know inside of x squared plus 1, that group right there, I'm going to place the square root of x plus 1. And as we know, squares and square roots kind of cancel each other out. All right? And in order for me to have an inverse, f of g of x must equal x, and x must also equal g of f of x. I can kind of already tell to have an inverse, but it's probably not going to work out. So this equals x plus 2. The domain of this is all real numbers. So you can write this way, x equals all real numbers, or you could do set notation, or we can do interval notation. All of these suffice. Now let's do g of f of x. So I have the square root plus 1, and I have x squared plus 1. When I simplify that, I have square root of x squared plus 2. Now, obviously, these do not equal each other. So f of x and g of x are not inverses. Since their compositions aren't equal. Since x plus 2 does not equal a square root of x squared plus 2. Now let's look at the domain of x squared plus 2. I just set that equal to 0, and set that equal to 0. And the domain should be, let's see, should be all real numbers. Should be all real numbers. Okay? It's gonna look something like, probably like this. I might be wrong. I probably should not guess, but I kind of want to. And it's because of that x squared right there. But you can look at a map of the graph to see that. So B, the last one, we have we're just inserting x plus 5 in the 2x minus 5. Okay, so 2, and inside we can write our g. Over here we have down here we have plus 5 over 2. So what does this look like? So let's do g first. We have x plus 5 over 2. 2's cancel. I get x plus 5 minus 5. This is looking good. I get x here. Domain here is negative infinity, positive infinity. Did interval notation. Let's go ahead and plug in f here. So 2x minus 5. This cancels. I get 2x over 2. And I get x. So since x equals x, f of x, and g of x are inverses. And lo and behold, their domains are the same. So the last thing on here is whether or not something's 1-to-1 or not. So remember, 1-to-1, it's symmetric about the axes, x and y axes, or just one of them. So this is 1-to-1. This is not 1-to-1. I cannot draw a horizontal line through it. My bad. I'm thinking about symmetry. But 1-to-1, if you draw a horizontal line, does it only hit one point at one y value, one height at a time? And here, it's not 1-to-1. Here, it's not 1 to 1. This hits, I can make a horizontal line through here, and it hits it 1, 2, 3, 4 heights. 4 different heights. I mean, four of the same heights for 4 different x values. Similarly here, not 1 to 1. This is 1 to 1. And this is 1 to 1. And that wraps up your review for topic 1 in unit 1.